All right, my friends, let's take a look. There are so many ways to solve inequalities and absolute value situations like what you see here in this first warm-up that I'd really love for you to be open to possibly a new way to solve them, because this is going to be a small part in a bigger problem, and you're going to want to be able to do these in your head. So look at how you solved warm-up number one. Hopefully you have a way that works. And so I'd love to introduce you to a way that could turn it into something that you could do in your head, or something you could do with just a quick little scratch work off to the side, and have it be like not a big deal. So if you're open to that, then kind of hang out here with me. So, and now that you're calculus students, you're probably more likely to kind of like be open to this idea. So first of all, if you see a subtraction between two quantities and then taking the absolute value of the result, basically what that means is like the difference between these two numbers, or the distance between these two numbers on the number line. So basically, for part A, I'd like for you to consider translating this little statement here, like this first part, as in your head, you would see it as the distance or difference, either way, between x and positive 2. And then the rest would just translate naturally as is less than 1, which it might help right now to think of it as less than 1 unit. And then what you could do is think of it either on paper or in your head as putting 2 down on the number line and then going a unit away up and down the number line for like your little boundary markers. So if you start at 2 as your anchor, and then you go up a unit and down a unit, and then basically your x values would be the numbers that are within 1 unit of 2. And so open circles on the 1 and the 3, because we're not talking exactly 1 unit away, we're talking within 1 unit. And so all the x values that would make sense here would be the numbers between 1 and 3, not including 1 or 3. I'm hoping that I can sell this to you, because it's the kind of thing that once you practice it a couple times, you can totally do it in your head. And honestly, this is kind of how, as calculus students, we should be thinking of notation like this anyway. If you think about the alternating series remainder theorem, for example. So with that said, for the solutions for part A, if you write it in interval notation, you would say x values that are in interval, or that are in the interval from 1 to 3, soft brackets on the 1 and the 3, because you don't want to include those values. So, all right, so if at the end of the day, if you like what you were doing and you're getting the same answers as I get with what you were doing, then go ahead and stick with that. But if you like this better, then feel free to, join me. Because you're going to be expected to solve these and solve these quickly, because they're going to be a small part in a bigger problem. Okay, so for part B, let's show. So the main issue you'll have with part B is you have a plus sign instead of a minus sign, but that's okay, because that's what double negatives are for. So adding 3 is like subtracting a -3. So if I rewrite the problem this way, then in my head, not something that, like in algebra, if I teach this in algebra 1, I make people write this sentence, but you're calculus students, so if you don't want to write it, just think it. So we would translate this to be the difference between your x values, or your solutions, and this time your anchor value is -3, and then we would say is less than 1 unit. Okay, so then thinking about a number line, if you start at -3, you're going to go up a unit to -2, and down a unit to -4, and you're looking for numbers that are within 1 unit of -3, and so it would just be these guys right here. And so your answer would be x values that are anywhere between -4 and -2, but you don't want to include -4 and -2. There you go. I hope you like this. Anyway, now for part C, that over 3 is definitely a little different. So for part C, what I would do is factor the 1/3 out. And these are things that I think we could all do in our heads if we wanted. And then you could multiply both sides by 3. And multiplying by positive 3 does not switch inequalities. So, and then translate it. So this time, without writing the sentence, I'm going to think it. So this is numbers basically that are within 3 units of 1. So here's your anchor value, positive 1, and you're going to go up the number line 3 to a boundary value of 4, down the number line 3 to a boundary value of negative 2, and you're talking about x values that are within 3 units of positive 1. And then that would lead you to say that your x values, the solutions to that original inequality, would be any x value between negative 2 and positive 4. There we go. Okay, I hope this is making sense. If you love it, use it. If you don't love it, but you have something else that gives you the same answers, then go ahead and stick with that. Either way. Okay. For problem 2, I'm going to go ahead and give a summary of the ratio test that would be helpful here. Let's see, how could I write this and make it go really fast? So I'm going to say, first of all, what you do for the ratio test is you always take the limit as n approaches infinity of a sub n plus 1 divided by a sub n. And then what you say about this, the series, has to do with the limit value that you get. So if L is less than 1, if this value right there is less than 1, then the sum of all the a sub n's converges absolutely. If L is greater than 1, then we'd find out that the sum of all the a sub n's diverges. And then, and this is going to become key in this lesson, if your limit value is exactly 1, then this test basically is inconclusive. Like you could get an L value of 1 on something that converges or something that diverges. And so we would say the ratio test is inconclusive. All right, I don't know if I saved a bunch of space by writing it that way or not, but there you have it. Okay, so we're going to come back to all of this stuff. So hopefully things are making sense. Okay, now for warm-up number 3, determine which x values make each geometric series converge. And if you weren't sure how to go about it, you could always fall back on if in doubt, expand it out. So like for part A, if n is 1, you get x. If n is 2, you get x squared, x cubed, x to the 4th, and so on. So hopefully now you could see what I meant by, is this thing, that this is geometric. So, and for what x values would it converge? Well, x is your common ratio for part A. So we'll just say your common ratio is x. And so remember, your common ratio had to be between negative 1 and 1 for your terms to go to zero fast enough for it to, add up to something finite. So, because your common ratio is x, if the absolute value of x is less than 1, then this thing will converge. And so, and notice, kind of notice that this is, if you want, you could replace x with x minus 0. This is me being extra nerdy, but sometimes it doesn't hurt to be able to do that. Anyway, so this would be saying, if I use the same method that I had been using before, that the distance between your solutions and 0 needs to be within 1 unit. And so there you go. That's how to be extra nerdy about saying that x has to be between negative 1 and 1. Anyway, possibly some unnecessary nerdiness there, but Okay, now before we move on, I do want to talk with you about some vocabulary, okay? So like the title of the section is a power series. And so I would say that we can apply the concepts that we're learning today about power series to pretty much any infinite series. In particular, something that has like an expression in terms of n as an exponent or a power. And so this would be an example of a power series here for part A. that just happen to also be geometric, but not all power series are geometric. I would say that pretty much all power series, though, like think they're geometric at the tail end, like when you get to the infinite part of the list, they start acting like geometrics in general, even if they weren't to start out with. Okay, so that's just in general what we mean by power series. So a series with an infinite number of terms where you've got an expression in terms of n as your power or your exponent. The next vocabulary that I'd like for you to be familiar with is an interval of convergence. For part A, this answer that we got here would be the interval of convergence. For this particular series here, because an interval of convergence is basically the collection of x values that would make your power series converge. So that's why this would be called the interval of convergence for part A. And then just some follow-ups. So your interval of convergence for this one would be from -1 to 1. Your radius of convergence, just kind of keeping true to like the definition of radius would be the distance from your center to, the outer edge. And so your radius of convergence here would be 1. And they do tend to use an uppercase R for radius of convergence for some fun reason. Sometimes they'll ask you where your interval of convergence is centered, and this one would have been centered at 0. So there you go. Anyway, that's the vocabulary that you'll need to be familiar with. So for part B, we will be finding the interval of convergence for this power series. And so how would I go about it? Well, what is the common ratio? This time I'm going to use the words instead of the letter. The common ratio this time, if you're not sure, you could always expand it out. But the common ratio this time is x minus 1 over 3. And we need that to be between -1 and 1. And another way to say that would be to say that its absolute value has to be less than 1. And maybe now you can see why I had you do that first warm-up, because we're going to have, in finding intervals of convergence, we're going to have a lot of setups that look like this. So then solving this is very repetitive. It's basically just warm up 1c again, but just to show like how quickly this could go, you could imagine factoring 1/3 out front in your head and then multiplying by 3, you'd be left with this. And then you know that this is saying you're looking for x values that are within 3 units of 1. And then whether you draw the picture or just think it out in your head is up to you. You do need to be pretty accurate though. So just choose something that will give you the correct answer, at least most of the time. Anyway, so for this one, we would say that the interval of convergence would be x values between -2 and 4. And then if you were asked, well, what's the radius of convergence? I hope visually it makes sense. Your radius was 3, which showed up here in your number line. It showed up there in your work as well. If you were asked, where is your interval centered? I hope visually it makes sense that it's centered at 1. So hopefully most of the stuff just kind of feels right and it doesn't feel like a ton of memorization. Okay, so now let's move on to the concept of the day, because so far I don't feel like you've really learned a ton of new stuff. But now let's kind of merge everything from this warm-up together. We're going to merge the idea of the ratio test with the idea of an interval of convergence together. And then we're going to be able to find intervals of convergence of power series that are not necessarily geometric, because right now we'd be limited to just geometric. So let's make it so that we could go beyond geometrics. So let's look at this ratio test here. So an interval of convergence is going to be the x values that make a series converge? Well, we know that if you were to get this to end up being less than 1, that you'd end up with something that converges absolutely. So what we're going to do is force that to happen, and we get to use some fun vocabulary and all that. So let's move on to the first example here, if I can find it. Okay, so example 1, I'm going to recycle. We already know the answer to part A because we just did it using the fact that it's geometric. But what we're going to do is pretend that we don't know that this one's geometric. And we're going to use the ratio test to determine the interval of convergence. And then we're going to state where this power series is centered and its radius of convergence. All right, so spoiler alert, right? We already know the answers. We already did this one. And the truth is that when you get to the AP exam, if they give you something that's geometric, I do hope that you just do what we did in the warm-up, which is a little simpler. But if it doesn't occur to you, then the ratio test will be there for you. Okay, so we're going to do this one together, and then we'll have you do part B on your own. So feel free to pause the video if you need a little time to copy the directions, or if you want to just wrap your mind around it on your own. But I'm going to go ahead and get started here. So if you have a power series that's either not geometric or you just didn't notice that it's geometric, then what you can do is enforce the condition of convergence of the ratio test. And we're actually going to say that to introduce our plan. You know that annoying word that they put on your AP test questions? They say explain or justify. This little sentence is going to take care of that. So we enforce the condition of convergence of the ratio test. And then a little colon that kind of says like, dun dun. Okay. Now, what is the condition of convergence of the ratio test? Let's look. It's that if you take the limit as n approaches infinity of the n plus 1 term divided by the n term, take the absolute value. If you get something less than 1, it definitely converges absolutely. So what would that look like if we did that with this problem? Well, this is how they're defining the nth term, right? So we would take the limit as n approaches infinity of the absolute value of x minus 1. Whoops, I guess, how do I want to write this? The quantity x minus 1 over 3 to the n plus 1 divided by x minus 1 over 3 to the n. And since we are enforcing the condition of convergence, we're going to say you need to be less than 1. Now, this is different than using the ratio test to see if something converges or diverges. We are saying you need to converge. So this expression has to be less than 1. That's enforcing the condition. Okay? And this is what you do when you're using the ratio test to find an interval of convergence. Okay, next thing is you simplify as much as you can. And I say let's just cancel as much as we can. So x minus 1 over 3 to the n can cancel out, and you'd be left with just one of them on the top. And so I'll just like replace that with 1. So what would we then have? This would yield the limit as n approaches infinity of the absolute value of x minus 1 over 3. And then we're forcing this to be less than 1. Now, fun fact, if n goes to infinity and there's no n in your expression, then as far as this limit is concerned, your expression is a constant. And so the limit as n approaches infinity of the absolute value of x minus 1 over 3 is x minus 1 over 3. And this should look super familiar. Anyway, let's factor the 1/3 out, multiply 3 by both sides. You should be ridiculously good at this by now. And you could draw the number line in your head or on paper. I usually just do it real quick. There we go. And we'd have an interval of convergence. Actually, you know what? Let's not call it the interval of convergence quite yet. Basically, we're thinking our interval of convergence is going to be from -2 to 4 and not including -2 to 4. And we are right, but I need to talk with you about a little detail that we're going to need to add in. We already know that the endpoints won't work because the sucker was geometric. And if your common ratio is 1 or -1, then it's going to diverge. But let's pretend we don't know that. And let's go back to the ratio test for a second. See how up here, if your limit value was exactly 1, the ratio test is inconclusive, and that means that that the sum could have been convergent or divergent. Either way, you don't really know using this test. And so let's say, for the example that we're on, let's say we don't realize that it's geometric, and so we don't know. These are the x values that would make this expression be less than 1. But there's this added step called checking endpoints. And follow me here. If we didn't realize this was geometric, then the endpoints, meaning -2 and 4, well, those would be the values that would have made your this limit expression be exactly 1. And if you're not sure what I'm talking about, let's just take a second and show that. So if this x right there was -2, then you'd have -2 minus 1, which is -3, over 3, which is -1, and then absolute value, and you get 1. And so you would have gotten exactly 1 here. And same thing with 4. If you plugged 4 in, you'd get exactly 1 as well. I'm going to put this stuff back. So when you're doing this ratio test work, you have to check the endpoints. So here's what that looks like. What would happen if x was -2? And what you do is you go back to the original problem right here, right there, and you just see what happens. Like, what would this say if x was -2? So it would say the sum as n goes from 1 to infinity of, and if x was a -2 right there, you'd end up with -2 minus 1 over 3 to the n. And then when you're checking endpoints, you just simplify. So we'd end up with, what would that be? -1 to the n. And then you could always expand it to see what you think it does. But you could see that this would be a geometric with a base of -1, and it would definitely diverge. So let's see which is a divergent geometric. Where your common ratio is -1. And so what that means is that we should not include -2 in our interval of convergence. We should leave this a soft bracket down here on the lower left, and we should leave this an open circle on the picture if you have a picture. Now let's check the other endpoint, and spoiler alert, it's also not going to work, right? Because we know that from previous work, but let's just show what it looks like to check it. So if x is 4, you go back to the original problem, my friends, and you just replace x with 4 and see what you'd get. So you'd get 4 minus 1 over 3 to the n. Simplify it. It simplifies to be 1 to the n, which if you expand it out is just infinitely many ones added together. So it is a divergent geometric, since your common ratio is 1. And so what that would mean is after doing the work to check endpoints, you would leave your answer the way it was with soft brackets on your x values, and now you could call it your interval of convergence. Okay. Now let's look at the directions. It says, determine the interval of convergence. We did. State where each power series is centered and its radius of convergence. That's where I really like this picture. So it is centered at x equaling +1. Hopefully that makes sense. And its radius of convergence was 3. You could see that on the picture. So hopefully things are making sense. And then this will be your answer right here. Okay, now I have kind of drug you through the mud on something that you had an easier way to do, right? Like this sucker was geometric, and in the warm-up, you had a way easier way to do it. The reason that I showed you this process is because part B will not be a geometric series. And so this will be the process that you'll use to find an interval of convergence and all that jazz. Okay, so with that said, I'd like for you to consider part B here. The sum as n goes from 0 to infinity of this big mess. Anyway, see if you can find the interval of convergence, where it's centered and its radius of convergence. Good luck.